Welcome to Calculus 1. In this lecture video, we're going to talk about what was an important topic in calculus called the area under the curve. Okay. The topic of area under the curve actually derived the concept of what we so-called a definite integral, which I would talk about that in the next lecture video. So to understand area under the curve, we need to first look at your sigma notation or summations. All right? The notation of sum is called the sigma notation. Okay, the Greek letter capitalized sigma. So the sum of n terms, okay, from the first term all the way to a sub n, will be written as the sum of I equal to 1 all the way to n of a sub I, where a sub I will be a sub 1, 2, 3, 4 all the way to n. So we're going to add them all up. So this is the way we will express it. So the I is called the index of the summation. A sub I is the ith term of the sum. And n is your upper bound, and 1 is here is your lower bound. Okay, so this is the way how we write summation of a sub I, and a sub I is the ith term, okay, in your summation. All right, so what we're gonna do here is just simply try some example of writing summation. So I need to write the summation from 1 to 6 of my I. So that will simply just be, the first term is 1, start off with 1, plus 2, plus 3, plus 4, plus 5, and the last term will be the 6. Okay. Alright. If I need to write the summation from the first term is 0 to 5. Okay, from 0 to 5 of I plus 1. So my beginning got to be 0. So that will be 0 plus 1. Plus the next one after 0, the ith term after 0 is 1 plus 1. And the next one after 1 will be 2. Still plus 1, because this plus 1 is always going to be there for this problem. Alright, so that's 0, 1, 2, 3. The next one after 3 is 4. The I is 4. And then the last one is 5. Alright, so if I simplify this is actually going to be 1 plus 2 plus 3 plus 4 plus 5. And then the last one, 5 plus 1, it will be plus 6. Okay. Alright, starting from 0 all the way up to 5. Okay, for the I plus 1. So if you can look at the difference between part A and part B, is that part B, you actually got 1, 2, 3, 4, 5, 6 terms, because the I will add on to 1. If you actually count your finger from 0 to 5, it's actually 6 fingers. From 1 to 6, starting with 1. 1, 2, 3, 4, 5, 6. Okay. It's very strange. Alright, I'm gonna write out this one. This one is very this one is a little bit funnier, but this is very important expression. We're gonna see a lot in a minute. Alright, start out with 1. Okay, all the way to n. I need to add up the sum of f of xi times delta of x. So that means the first term got to be f of x sub 1 delta of x. The next term got to be f of x of 2 times delta of x, and plus dot 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 plus Okay. I'm not gonna write the last one yet. I'm gonna write the one before the last one. The one before the last one got to be f of x sub n minus 1. Okay. Times delta of x plus the last one got to be f of x of n, the nth term, because I need to add up to the last term, times delta of x. Okay, so the one before, my notation will simply be minus 1. Alright, so this is the way how we write out summation. We're not really going to write them all out for other problems, because we can actually formulate, okay, some of these summations. So let's take a look at a couple of properties in our summation formulas. If I have a constant k, I need to times my a sub I, and I need to add up from 1 to n, we can actually pull out that constant k and just isolate the a sub I. Alright. Another important property we will use in this video is if I need to add from 1 to n of a sub I plus or subtract another b sub I can actually separate them out. Okay, I can actually separate them rather as sum of I to n of a sub I, add or subtract, in the sum of 1 to n of bi. I can actually split them up into two separate summations. Okay. Alright, couple basic formulas here, very important. We will refer back to this formula quite a bit. Okay. Alright, if C is a constant, okay, if summation is a constant, we need to do it from 1 to n. We will simply, okay, take the n times the C, or the constant times the n. Alright. Summation of I adding from 1 to n can actually be formulated as n times n plus 1 divided by 2. Alright, for the I square, okay, that will be summation of I square from 1 through n will be n times n plus 1 times 2n plus 1 over 6. And this one is for 1, 2, 3, 4. This is the fourth one. And this I to the third would be n squared times n plus 1 squared over 4. So I'm not going to really show you exactly how they derive this, but what I can point out to you is that very first example. If we will add up if we'll add all this 1 through 6, okay, that will be the same thing if I will say 6 is my n times 6 plus 1 divided by 2. Okay, that will actually equal to the same sum. Alright, got a lot to do with idea of a trapezoid. And I learned this when I was very little. So basically what it's saying is you take the first number, add on to the last number, which is 7, and you times the height and divide it by 2. So it's a lot like the trapezoid, okay, where we will add the two bases and then times the height, which is a 6 right here, and then divided by 2. And the divided by 2 part is referring to the median of the trapezoid. Okay. Alright, so that's a little bit away from what we want to do here. So I'm gonna do an example here. Okay, use the summation formulas above to rewrite this expression. Okay, and at the end we're gonna do some evaluating. Okay, and begin to see the, and I'll begin to trying to make the important concept as we go along here. Alright, so summation of 4i plus 3 over n squared from 1 through n. So So what I can do is I can put out this n squared, okay, in front of my summation. So that will give me 1 over n squared times the sum of I equal to 1 through n of just 4i plus 3. Alright, so the addition here allow me to split my sum into 2 pieces. So we will write this as 1 over n squared, the sum of 1 through n of 4i plus the sum of from 1 through n of 3. Okay, so basically I'm gonna add up the 2, then times by this 1 over n squared. So I'm gonna put these guys in the brackets. Alright, so this is gonna be 1 over n squared. So I'm gonna turn this I into the n times n plus 1 over 2. So that will give me 4 times my I, which is n times n plus 1 over 2, plus, okay, 3 here is a constant, so that would just be the n times the 3, which is 3n. Okay, then I will simplify this. I believe this 2 can cancel out and leave me with a 2. So 2 is on top. 2n times n plus 1. So 2n times n plus 1 plus 3n. This 3n is on top as well, because I don't have any more denominator. So that gave me 2n squared plus 2n plus 3n. So that will be 2n squared plus 5n. Now 1 over n squared will now times 2n squared plus 5n. So now my 1 over n squared will distribute. 1 over n squared times 2n squared. The n squared will cancel out, top and bottom. That just leave me with a 2. Plus, okay, the n on top and this n squared in the bottom. One of them canceled out, so they leave me with an n in the bottom. My 5 stays on top. Okay, so this will be my simplified expression: 2 plus 5 over n. Alright, so quickly here, I'm gonna do some evaluating. Okay, I want to do some evaluating. So let's say if n is 10, okay, if I want to add up from 1 to 10, what I can do here, I'm going to just use a calculator, very basic. I'm going to say 2 plus 5 divided by, you know what, I'm going to put this in a parenthesis, 5 divided by 10. Alright, that gives me 2.5. Alright, I'm going to turn my n a little bit bigger, let's say 100. I'm going to keep on making the bottom a little bit bigger. 2, this is second enter, turn that into 100. 2.05. Alright, let's do n equal to 1,000. Let's see what happened to my answer. 1,000. 2.005. Okay, so you can kind of see as n increases, okay, 10,000. As n increases, okay, the limit of my expression is actually approaching to 2. Okay, and that's a very important concept throughout this whole video. as this n increases going to infinity, what that tell me is my final sum will actually become a 2 for this expression. Okay, so if I will add up from 1 through a million or a trillion, okay, my final answer, my sum will actually converge to a 2. Alright, so what does summation got to do with area under the curve? So this is how it goes. Alright, starts you off with an approximation here. Let's say we want to approximate the area of a plane region. Okay, so I'm going to use what we so-called the left and right endpoint in a given number rectangle to find 2 approximation of the area of the region between the graph of the function and the x-axis over the given interval. So I already drew the picture for you. Okay, so my function is negative x squared plus 5. I only want to look at it from the interval from 0 to 2. So what I'm going to do is, this curve is negative x plus 5, and I already set my window from 0 to 2. I want to use 5 rectangles with equal width, just for the convenience of my calculation here. Okay, so if I want to use 5 rectangles of equal width, okay, so that means the width of each rectangle, okay, got to be 2/5. The width of each rectangle got to be 2/5. Okay, so as you can see, from 0 to 2/5, okay, the width is 2/5. All right, the concept of right endpoint. Okay, the right endpoint. So the rectangle I drew here, okay, the right point of the first rectangle is right here. So that point goes straight down to the x-axis 2/5. So if I will pick the third interval, okay, I say the width is 2/5i, because if I will do the third interval, 2/5 times 3 will be what? 6/5. Okay, so the width is 2/5i at a time. Okay, so my first right endpoint will be 2/5. The next one is 4/5, 6/5, 8/5, and 10/5. Alright, so to find the area of the rectangle, okay, we take the height times the width. So this height, how tall is this rectangle on the curve? That got to be the y value, okay, of the function. So if I take this 2/5 and plug into the function, the y value here, okay, got to be my height. And all I'm going to do is take that height times the width. And we can quickly figure it out too, just for this first interval. So if I say negative parenthesis 2/5 squared plus 5, okay, my y value is 4.84. Okay, so that's my height. The width is 2/5 at the time, so times by 2/5. So the first rectangle, the area of the first rectangle is 1.936. So we're going to add up the sum of all these rectangles. Okay, so my height is where I will substitute the 2/5 I into the function, where I is 1 through 5, because I got 5 rectangles here. Okay, so what we want to do here is add up or sum up from 1 through 5, from I equal to 1 through 5 of all the height times the width. Okay, so rather than do this one at a time then add them up, I'm gonna go ahead
Okay. Basically, just add up all of them simultaneously. So basically, I'm gonna try to simplify this expression I'm about to write. Okay, where the summation is a little bit easier to evaluate toward the end.
Alright, so the height is f of 2 over 5i. That's where I will evaluate, evaluate the x value, at the right end, the right endpoint. Every x value at the right endpoint, is called 2/5 I. I'm going to put it into my function. So this is going to be sum of I equal to 1 through 5. My height is f of 2 over 5i times the width. Every width is equal, so every width is 2/5 at a time. Alright. So this part right here is what we're gonna substitute into the function. So that will give me the sum. Let me write it right here. So that will give me the sum of I equal to 1 through 5. Substitute 2 over 5i for x right here. So that will be negative 2 over 5i. Oops, excuse me. Squared plus 5. So this whole part is my function. I'm gonna put in the bracket because don't forget I gotta times the height, excuse me, or times the width of all the rectangles. Alright, so from here, this plus on here allow me to split up my summation. So I'm gonna have the sum of I equal to 1 through 5. This part is 1. Negative 2 over 5 squared is negative 4 over 25. I'm gonna put that 4 over 25 up front, along with that negative sign here. So that'll be negative 4 over 25. And that will allow me to isolate the I squared here. Plus the 5 part, which is the sum of I equal to 1 through 5 of 5. So all these guys are going to eventually times by 2/5. So what I can do is I can go ahead and distribute the 2/5, put them up front. But right now I just want to kind of focus on the I squared part. Alright, this first sum in the bracket, negative 4 over 25 times I squared from the formula earlier is n times n plus 1 times 2n plus 1 over 6 plus this second term here in the bracket. 5 is a constant, so we take the n times the 5, which will give me 25. These two terms in the bracket will get multiplied by 2/5 at the end. So there's a different way to go about simplifying this. Alright. My n was 5 this whole time, so I'm going to put 5 right here. So that's negative 4 over 25 times n is 5 times 5 plus 1 is 6 times 2 times 5 is 10 plus 1 is 11 over 6. And plus that 25. Alright. Put them in the bracket. Times by 2/5 at the very end. Alright, I think 6 can cancel out. 5 and 25 cancel out, leaving with a 5 down here. So what I got on top is negative 44 over 5 plus 25. Times 2/5. Alright, negative 44 over 5 plus 25. 5 times 25. And add on to the negative 44. 5 times 25 is this, plus negative 44 is 81. So that will be 81 over 5 times 2 over 5. And if I put this in the calculator, I think it will be exactly 6.48. Okay, so that's the area, okay, of my 5 rectangles. Okay. Alright, so the problem here is these rectangles are underneath the curve, okay? So all these white parts that's under the curve, I actually did not include them. So what we can do is draw another set of 5 rectangles, okay, that are above the curve. Oops, sorry, went too far down. Okay, so we call those the left endpoints. So you know, if I would extend my rectangle here, my very first rectangle, okay, if I would pick the left endpoint and go and draw a rectangle here, for the second one, from the left endpoint, okay, draw another rectangle. Okay, from the left endpoint, draw a rectangle. That will actually include all these white parts. Okay, so that's why the topic here, the instruction here says use the left and the right endpoints. Alright, so these are the left endpoints of the 5 rectangles. Okay, so this point right here is the left endpoint of the second one. This is the left endpoint of the first one. So this time my width is actually 2 over 5 times I minus 1 instead of 2 over 5 times I. Okay, and here are my intervals. I still got 5 intervals. I still got 5 intervals here. Okay, and you can come think of it that the first one, the left endpoint is a 0. So if we actually plug in 0 into, you know, as for the interval here, alright, the very first interval I is where is 1. 1 minus 1 is 0. 0 times 2/5 is 0. Okay, so you really have no width here. So technically speaking, this is only 1, 2, 3, 4. 4 left endpoint compared to the 5 right endpoint earlier. That's why this got to be an I minus 1. Alright, so here are the left endpoints for the intervals. To find the height of each one, we will plug in the width, 2 over 5 times I minus 1 into the function. So let's do the same thing as we done earlier. And you can kind of see that this answer, this
phi rectangle here, that one above the curve, okay, is going to be bigger than the one that was under the curve. Alright, so let's write it out. I, the sum of I equal to 1 through 5. My height, f of 2 over 5 times I minus 1 times the width, 2 over 5 times I minus 1.
Oh, excuse me. The height is still 2 feet. I don't know what I'm writing here. The width is still 2 feet when I write it out. Because they're all equal width still. Okay. So the left endpoint of any one of these left endpoint, okay, got to be 2 over 5 times I minus 1. So if you take a look at the last one, which is the 5th rectangle, 5 minus 1 is 4. 4 times 2 is 8. So that's why this one is the very last one, 8 over 5. Alright, so if we will take the a over 5, okay, the left endpoint, the very last one, we substitute this a over 5 into the function. Okay, so that's why I still write 2 over 5 times I minus 1 for my height. Alright, substitute 2 over 5 times I minus 1 back into the function. That was negative. Okay, x squared. So my substituting 2 over 5 times I minus 1. That's my x. And that got to be squared. Don't forget plus 5. Alright, and these guys were times by 2/5. Okay, so to help you out, this is negative x squared plus 5. Okay, that's the function. Alright, this one is a little bit harder. This one look a little bit more complicated. Well, I'm going to pull out this 2 over 5 squared, which is negative 4 over 25 again. So this is going to be sum of I equal to 1 through 5 bracket negative 4 over 25 times I minus 1 squared and the reason why I did not put this up front is because I'm going to expand this I minus 1 squared in a minute. Alright, plus, but I'm going to go ahead and, since this plus sign is here, I'm going to split up the two sums. So if I don't, I'm going to think this 5 will actually add on to all these with the i's. Okay, I don't want to do that. It'll throw me off a little bit. Times 2/5 here. Alright, so I minus 1, the whole thing squared, will give me I squared minus 2i plus 1. See, these three terms all got to be multiplied by negative 4 over 25. Okay. So of I equal to 1 through 5 plus equal to 1 through 5 over 5. You know what? I'm gonna move this bracket here out. So that's actually more mathematically correct. There you go. That's more like it. Alright. So -4/25. Okay, multiply all these terms. I'm gonna go ahead and open up my I squared here, 2 and the I. And since these guys are adding and subtracting, I can split up more and more sum. So there will be sum of I equal to 135 of -4/25 times I squared, and I squared becomes n times n plus 1 times 2n plus 1 over 6 minus, you know what, if I'm going to open it up, if I'm going to go ahead and open up this I squared, I don't need this summation anymore. I'm going to move these guys over. Minus 2 times I is n times n plus 1 over 2 plus, oh, see, I don't forgot, I'm skipping step, I don't forgot my -4/5 times the second term here, so that would make this term positive. Alright, -4/25 times 1. No, make this term negative. So that's -4/25. This is a constant inside for the sum, so that will be times by 5. Because n times 1 is 5. Plus, okay, I don't want to get these guys all jumbled up. This is a whole separate sum, so I'm going to do these guys together. 5 times 5 is 25, and all of them need to times by 2/5 at the very end. Alright, so let's simplify what's inside this parenthesis with a -4/5. Anybody can be simplified here. N is 5, so I'm going to go ahead and write it out. -4/25 times n is 5 times 6 times 11 over 6. 5 here will become 11 plus 4/25 times 2 times 5 times 6 over 2 minus 4/25 times 5, and I will add the 25 in a minute, and then afterward everybody times 2/5 the width. Alright, so from here it's pretty easy. This kind of canceled out. That leave me with a 5 again. So this first term is -44 over 5 plus 2 and 2 cancels out. That leaves me with a 5 down here. So that's 4 times 6, 24 over 5 minus 4/5, I believe. Okay, these two can be reduced, and these guys will then add on to that 25 and then get multiplied by the 2/5 at the very end. So since the LCD are the same here, there will be -44 plus 24 minus 4. -24 over 5 plus 25 times by 2/5. 5 times 25. 5 times 25 is 125 plus a negative 24 is 101. So 101 over 5 times 2/5. That'll give me 202 over 25. And if I put this in the calculator, that'll give me exactly 8.08. So my approximation, the area under the curve, got to be between 6.48 from the what was that? From the right end and the left end. Is 8.08. Okay. So my area under the curve got to be between these two approximations. So again, what will happen is if I will increase my n, remember what my n is. Okay, my n is 5, and that's 5 is referring to the 5 rectangles. If I will increase my rectangles, increase my n, okay, the more rectangles I have, the closer my approximation gonna be, okay, to the true area under the curve. All right. Now let's take a look at the concept here, okay, called the upper sum and lower sum. So what we just did, okay, the procedure that we went through earlier, okay, can be generalized as follow, and that will lead to what we so-called the upper sum and lower sum. Alright, so first thing first, our function f of x got to be continuous on our interval from a through b on a closed interval. Alright, the subdivide the interval a through b into n subintervals with equal width. Alright, so earlier we looked at 5 subintervals of equal width, or 5 rectangles. So delta of x, okay, which is referring to the width, is b minus a over n. Okay, so n is our interval. Okay, b is the one end of the closed interval. Subtract the beginning of the closed interval. So this is going to be our width. Alright, the endpoints of the intervals. Okay, what's confusing is about the endpoints, the right endpoint, the left endpoints. Okay, but if you really think about the endpoints, it actually duplicates after a while. If I will go back to our previous example, okay, you see the 2/5 here in the second interval. That's the left endpoint. But that's the left endpoint is also the right endpoint of the first interval earlier. Okay, so with these numbers being here, we can basically generalize them as your beginning of the interval a is equal to x of 0. So whatever a is plus 0 times delta of x over the width. All right, the next one. The next endpoint, okay, will be the beginning a plus 1 times delta of x. Okay, so we can go from 1, 2, 3, 4 all the way to n, however many subinterval we're gonna have. Okay, because the last one is called the x of n, which is equal to the very end of your closed interval. So, if you looked at the one earlier, I believe earlier our previous problem, we are bounded by from 0 to 2. Okay, so my x of n is equal to b, which is 2. Start out with 0 plus 5 subintervals times the width, and the width is 2/5. So 5 and 5 canceled out. That's how I get my last number is 2. Alright, now because f of x is continuous, okay, like we talked about on number 1, by the extreme value theorem, it guarantees the existence of a minimum and the maximum value of the function in each sub-interval. Okay, so what that means is, if I will go back to my right endpoint, you know what? Let's go to the left endpoint. If I will look at the interval, if I will look at this rectangle, wrong color. If I will look at this rectangle here, take this rectangle for example, any rectangle, okay, but by the extreme value theorem, it guarantees it. Inside that one rectangle, you're gonna have a maximum value and a minimum value. Okay, within that rectangle. Okay, in each sub-interval, we're gonna have one. So this becomes the max. That's the min for the next. Okay, for the next rectangle here, or the next sub-interval. All right, so. Okay, those minimum value or maximum value we denote it as f of lowercase mi or capital letter mi. Those are the heights. They're also basically your heights of the function in the ith sub-interval. Okay, any one of those sub-interval that we choose. All right, and earlier when I drew the rectangles, okay, underneath. Okay, my curve, that's called the inscribed rectangle. So inscribed rectangle is lying inside the ith sub-region, or circumscribed rectangle is extending to the outside of the ith sub-region. Okay, so all that's saying is rectangle above the curve or underneath the curve. Call it inscribed rectangle or circumscribed. Alright, so the sum of the area of the inscribed rectangle is the lower sum. Alright, so that means my left endpoints were the circumscribed, my right endpoints were the inscribed. Alright, so that's why the 6.48 earlier is called the lower sum. Alright. 8.08 is an upper sum. Upper sum come from circumscribed rectangles. Okay. Circumscribed rectangles. Alright, so our lower sum earlier, okay, the lower sum can be written as lowercase s of n is equal to the sum of from 1 through n of f of mi times delta to x. Okay, so we can find all the minimum value, okay, of those rectangles earlier. Okay, each rectangle carry a minimum and a maximum. We can add up all the minimum values times by the width, and we can also add up all the maximum value times the width, and that will give me my upper sum. Okay, and here's a picture. Okay, if we pick any sub-interval, ith sub-interval, that interval, that rectangle has a maximum value and a minimum value. Okay, so the I here stand for any one of those sub-intervals. Alright, so let's try another example here. I'm gonna find the upper sum and the lower sum. Okay, and I wrote out a few things and I draw the picture already to help us to comprehend it better. Alright, my function is x squared. Okay, I'm gonna do from
close interval from 0 to 2 again. Since the function is increasing on the interval 0 to 2, if we grab x squared and just look at from 0 to 2, this function is actually increasing. The minimum value on each subinterval occurs at the left endpoint. The minimum value is on the left endpoint. Left endpoint is blue. So if I would look at the second rectangle, okay, the left endpoint is blue. The maximum for the second interval here is the red point right here. So the maximum is at the right endpoint. The minimum is occur at the left endpoint. Okay, it's kind of confusing because every subinterval contains a maximum and minimum. Okay. Alright, so let's take a look at the left endpoints. Remember, the left endpoints are the blue. So if I count how many I have, okay, how many left point I have, I'm actually one short compared to the right endpoint. Alright, so my left endpoint minimum is A plus okay, 1 times delta the x. Alright, when I wrote this 1 right here, that's referring to, okay, that's referring to one rectangle. It's not the very first one, it's actually the second one. Okay, so this 1 can be any number here. It can be the second, the third, the fourth interval. Alright, so that's why we denote it as I minus 1 times delta the x. And we can find delta the x by taking the 2 minus the 0 divided by n subintervals. Okay. Alright, so if I just count, okay, 1, 2, 3, 4. If I just count, pick that one. Alright, that would be 0 plus 4 minus 1, which is 3. This is the fourth rectangle, but my left endpoint, 1, 2, is only the third one. Okay, my minimum is only the third one. Okay, that's why this I minus 1 here makes sense. Alright, so my I minus 1 times my delta of x, okay, 2 over n. So that'll just be 2 over n times I minus 1. Alright, so my lower sum, okay, sum up all the minimums basically. It's gonna be from 1 through n of f of lowercase mi, the sum of all the minimum times their width. Okay, again, I'm using equal width for all these subintervals. Alright, so let's write it out. F of mi. F of mi. My mi is 2 over n times n minus 1. So f of 2 over n I minus 1 times my delta of x, my width, 2 over n. I'm going to substitute this into my function to evaluate all the heights. X squared, so that will be sum of 1 through n of x. This is my x. I'm going to substitute squared times the height, 2 over 5. Alright. Alright, so let's take a look.
not 2 over 5, 2 over n. Oh Lord, I'm still thinking about earlier. Alright, there's a way to do this. We'll make it easy, okay? Alright, I'm gonna take out this 2 over n. 2 squared is 4, and that 4 times this 2 will be 8. Over this n squared become n squared times another n back here. Eventually it will be n to the third. Alright, so that will isolate the summation of just I minus 1 squared. Alright, so if we multiply it out, this I minus 1 squared, a over n to the third still up front. It will be I squared minus 2i plus 1. Alright, I'm going to go ahead and deal with this. So I'm going to split up as 3 different sums. Okay, at the same time, I'm also going to expand my I squared as well. So this 8 over n to the third stays up front times bracket. Okay, the I squared, if I expand it, become n times n plus 1 times 2n plus 1 over 6 minus 2 times I is n times n plus 1 over 2 plus n. N times 1 is just n. Alright. So let's see if we can clean this up a little bit. Now, I'm not saying, okay, I just realized that I'm not saying 1, 2, 3, 4, 5, 6. I'm not saying do 6 rectangles, okay? I'm actually telling you using n number rectangles here. Okay, I just draw 6 of them to kind of show you these endpoints. Alright, I know this will cancel out. That just leave me with n times n plus 1. So my LCD between the 3 terms would just be 6. So that will be n times n plus 1. 2n plus 1 minus LCD is 6, so that will be 6 times n plus 1 plus 6n. Holding over 6. Alright, so let's do this part right here. The n plus 1 times 2n plus 1, I believe is 2n squared plus 3n plus 1 times by the n up front. That gives me 2n to the third plus 3n squared plus n. Negative 6n distribute is negative 6n squared minus 6n, and then like the last plus 6n. Holding over 6. And I will get multiplied by a over n to the third. Alright, so let's see what we can combine. 2n to the third combined with nobody. 3n squared minus 6n squared, negative 3n squared. Minus 6n plus 6n cancel out. That gives me plus n over 6. Okay, multiplied by a over n to the third. Alright, so let's simplify some more. And here I'm going to skip over several steps here, okay? I'm going to just kind of talk it out with you. Alright, if we reduce this 2, that will give me a 4 and a 3. So practically I have 4 4 over 3 n to the third. It's gonna times all these 2n to the third minus 3n squared plus n. So if I do a distribution, for the first term here, the n to the third will cancel out. 4 times 2 is 8 over 3 minus 3 and 3 cancels out. N squared n cancels out. So that'll be 4 over n. N and n to the third cancels out. That'll be plus 4 over 3 n squared. Okay. So that was my lower sum. Alright, let's try one with the upper sum. So if we say the upper sum, okay, or the maximum, the right endpoint, let's say the right points are I at a time. So then this will be 2 over n times I rather than I minus 1. Because the left point is 1 short. Okay, you can say 1 short. It's one way to think about it. Alright, so mi, the maximum, the right endpoint will be 0, your a, plus, okay, any interval times by delta of x, 2 over n. So that will be 2 over n times I. Alright, so your upper sum, okay, will be f of mi times delta of x. So let's substitute back into our function here. Alright, so substitute my mi into my function. That will be 2 over n I whole thing squared, because it was x squared, times the width. Okay, this is just 2 over n again. The delta of the x that we wrote earlier. Yeah, we wrote delta of x at 2 over n. Alright, so just for the convenience here, 2 squared again is 4. 4 times that 2 is 8 over n squared is n squared times n again is n to the third. Okay, pull that out in front of the summation. So that allows me to isolate just my I gotta be squared. Alright, so I'm gonna expand my I squared. So that will be n times n plus 1 times 2n plus 1 over 6. I'm gonna go ahead and reduce this just like I did earlier. That's a 4 and that's a 3. And I believe earlier when we multiplied all this stuff out earlier, this is 4 over 3n to the third. All that going to become 2n to the third plus 3n squared plus n. So this time, if I take my 4 over 3 into the third and do distribute, that will again give me a over 3 plus 3 and 3 cancels out, n squared, n to the third cancel out. That leave me with 1 n in the bottom, 4 on top, plus n and n to the third cancel out. That leave me with 4 over 3 n squared. Okay, so that's my upper sum. Alright, so the upper sum and lower sum will be different based on what the whether the function is increasing the interval or decreasing on the interval. So I show you both examples now so far. So hopefully just keep an eye on that when you try some of these problems in the study guide. Alright, so I'm gonna go back to the lower sum real quick. I'm gonna copy and paste it. So imagine
if I will increase my subintervals, okay, if I will increase my subinterval n as many as I can, as n approaches infinity, as the number of subinterval increases, both your upper sum and your lower sum will actually be the same. Because 4 divided by a real big number is 0. 4 divided by something even bigger is 0. So all these fraction part with the n in the denominator will all become 0. Therefore, the upper sum and lower sum are actually gonna equal to each other, a over 3. So that tells me that the area under the curve for this problem is actually a over 3 in that interval 0 to 2. Okay, so that inspires, okay, our next topic, which is the limits, okay, of the lower and upper sum. Alright, so I'm going to take a break here. Okay, I will split this video into 2 parts, and we'll talk about the upper and the limits of upper and lower sums. Alright, thank you for watching. We'll pick back up on the next video from here.